Okay, so now we have the free response question, and I really like this question. I think it gets to a lot of really good conceptual ideas and helps us just, get a good conceptual understanding of all the topics in this unit. So we start off, we say two identical spring scales are each attached to a cord that is wrapped around a pulley as shown below. The two pulleys have identical masses MP and radius r sub p. However, pulley A is a solid disk, whereas pulley B has most of its mass located at its outer rim. Both pulleys can rotate about their centers with negligible friction in their axles. So we're pulling down with the same amount of force. It says the pulleys are initially at rest when the two spring scales are pulled with the same constant force F spring or Fs, causing both pulleys to rotate. Predict which of the pulleys, if either, will complete one revolution first. So let's think about really what's different about these two. So we know that torque is equal to I times alpha, and these both have the same torque on them. They have the same radius and the same force, and so we know this torque is going to be the same. And the thing that's really going to help us figure out which one will complete the revolution first is really based on this angular acceleration. They start off from rest, and we want to know pretty much which one will get faster at a faster rate, so it'll be able to spin through this angular displacement. So we're really looking at which factors will affect the angular acceleration. So we know that the rotational inertia is really going to be the deciding factor. That's what's really different about pulley A and pulley B. And the rotational inertia is really just a measurement of how spread out our mass is. So in this case, they have the same amount of mass, but pulley B is really far away. Most of the mass is concentrated on this outside rim, whereas with A, the mass is nice and evenly spread out. So we have a lot of mass kind of closer to this axis of rotation. And if we think about kind of what we do with rotational inertia, the fun stuff with it, like if we take those weights and we're standing on the platform, if we hold them far away from ourselves, we know it's kind of harder to move. But if we bring them closer, it's going to be easier for us to spin. So if our mass is more centrally located, if it's closer to the central axis, then I is going to be less. So we see in this case, pulley B has a greater rotational inertia than pulley A. So because of that, we're saying, okay, well, the amount of time it takes to spin is based on the angular acceleration. Because pulley A has a lower rotational inertia, and the rotational inertia is inversely related to the angular acceleration, because we have a lower rotational inertia, pulley A will be able to complete its revolution in a shorter amount of time. So let me kind of rewrite that really quick. Let's rewrite it as this. Alpha equals torque divided by rotational inertia. So we see these are inversely related to each other, or we could rewrite it as I equals torque divided by alpha. But we see, hey, if I goes up, it's going to decrease, if angular acceleration goes, if this goes down, angular acceleration is going to go up because they're inversely related to each other. So because the angular acceleration is dictating how much time it's going to take us to rotate, how much time it'll take us to speed up, and then eventually complete that one full rotation. Because it's related to I, if the I goes down, then we'll get there quicker. So A will get through that rotation quicker. And then deriving the equation. So this one I kind of went ahead and did already, but so deriving an equation for the time TA, it takes pulley A to complete one revolution. Let IA be the pulley's rotational inertia. Express your answer in terms of force spring, IA, MP, RP, and physical constants as appropriate. Type your complete equation below. So here we can start out and say, well, this system is being torqued. And when it's being torqued, we say, well, torque is just the force times the distance that that force is acting from the center of rotation. So in this case, we have the force spring that is acting at our radius, RP, away from this center of rotation. So our torque is equal to force spring times R pulley, and we can set that equal to I times alpha using that Newton's second law for rotation. And now what we really want to do is, well, we want an equation to think about one complete rotation, but all we really have that deals with our kinematics is this alpha. So what we need to do is think about how can we sub in, how can we get alpha to kind of show up as time for a complete rotation. So how can we get this kinematics ideas in here? Well, we can use our kinematics equations. So the one that comes to mind for me is, well, we have this equation from regular kinematics, linear kinematics. It says x equals x naught plus v naught t plus 1/2 at squared. And we said, well, the same thing applies for rotational kinematics. So I know that my angular displacement, this theta, is kind of the same as my linear position. So I'm going to replace x with theta, and say, well, v naught is the same as my my angular velocity. It's the same kind of idea. So I'm going to replace rotational velocity, omega naught t, plus 1/2 alpha t squared. So replace linear acceleration with angular acceleration. And now I can kind of plug in what this problem is dictating, what this problem wants. I know that I start from rest at this kind of 0 location, so this doesn't really matter. We can call it 0, and I'm starting from rest. And I know that I want to figure out for one full rotation. And we know from math and from other stuff that we've done that one full rotation is going to equal 2 pi radians. So for my angular position, I want to end up at 2 pi radians. And I can set that equal to this 1/2 alpha t squared. And again, I really want to solve this for alpha because I need to plug in. I want to get time into this equation, so I need to just solve this for alpha. So I can say, okay, let's multiply both sides by this, or divide by 1/2, so multiply both sides by 2. 4 pi equals alpha t squared. Alpha equals 4 pi over t squared. And now let's sub this in. Again, we want time in our equation. We want to know the time for one full rotation. So we can sub in this alpha, and then just kind of rearrange everything we have over here for time. And we end up with this equation. 2, I could just kind of pull out, right? We square rooted, so I pulled out the 4 and said, well, the square root of 4 is just 2, so I can pull that out of my equation. And I get IA times pi over Fs over Rp. And that's an equation for time. So how much time it takes for one rotation. So time for a rotation. So it's a very specific time, the time for one rotation in this case. And then we say, okay, is this consistent with my answer to A? So in A, I said, well, I really argued from this position that if my rotational inertia is going to be lower, it'll take me less time for one rotation. So if I have a lower rotational inertia, my time will be lower. And I see, yeah, this works out. In this case, my time is directly related to the square root of IA, to my rotational inertia. So that works out because the time is directly related to the square root of rotational inertia. If this quantity, if we had it in an equation, if this quantity went down, my time would also go down. So this is consistent because of that relationship that we found in the equation. All right, for C, a block of mass m is attached to pulley A as shown in the figure below. The block is released from rest. Describe how the net torque exerted on the pulley and the magnitude of the angular momentum of the pulley are changing, if at all, a short time after the block is released. All right, so we got the situation, and we just want to know about the torque and the angular momentum. So we say, okay, well, torque is just going to be the distance from the pivot point times F. In this case, because the rope is still constantly on this outside, and the rope still has this force from this tension, the force is definitely not changing, right? This mg down, and then the tension up, some sort of relationship between those two, we don't really know. But this torque on the outside caused by this tension force, it's not changing. We're not changing the mass, we're not changing anything about the force. So the force is staying the same, and then the distance is staying the same. We're not changing this pulley, nothing about the distance is changing. So our torque is going to be the same thing because r is the same and F is the same. For angular momentum, we're saying, well, angular momentum, what we can think of is we say, okay, if we look at our system, if there's an outside torque acting on our system, then we have a change in angular momentum. That's dictated by this equation. So in this case, the system is just the pulley. So do we have an outside torque acting on this? Yeah, we're getting an outside torque from this mass. This mass is causing a force at some distance rp, away from the axis of rotation. So we do have an outside torque acting on our system, which means we do have a change in angular momentum. It's going to be increasing. We're going from rest to some angular velocity, so we're going to have this increase. And we're really just looking at the magnitude, so technically, yeah, it's going in the clockwise direction, so technically that's a negative angular momentum, but we just want to care about the magnitude, so yeah. And then for the final part, a long cord of negligible mass is wrapped around a third pulley, pulley C, and attached to a spring scale as shown in the figure below. The spring scale is pulled downward so that it exerts a constant force of magnitude Fs on the cord As the spring scale moves down a significant distance, the vertical portion of the cord moves closer and closer to the center of the pulley. Predict how the net torque exerted on the pulley and the rotational kinetic energy of the pulley will be changing, if at all, as the spring scale moves downwards and the vertical portion moves closer to the center of the pulley. So in this case, if we're looking at the torque, well, we said torque, our equation for torque is r, so the distance from the center of rotation, times f. In this case, we have the same f. F is going to be the same because we have the same setup, we have the same constant spring scale, but in this case, the distance from the center of rotation where that force is acting is actually decreasing, right? We have this string, it's unraveling. Over here we start all the way far away. By the time we get to this point, r is going to be really, really small. So we actually see the situation, r is decreasing, f is staying the same, but because r is decreasing, the torque is actually decreasing. And then we're looking at rotational kinetic energy. So in this case, we said, well, even though torque is getting smaller, even though torque is decreasing, it's still acting positively on our system. It's still adding energy to our system. It's still doing this work on our system. We said, well, like work is traditionally force times displacement. In this case, we can call it torque times displacement, I guess angular displacement. The angular displacement is always in the same direction, and the torque is always positive. The torque is not like negative, it's not changing signs. So the torque is always acting in the same direction. We also have this angular displacement in the same direction. So the rate of increase of rotational kinetic energy won't change or won't be increasing, but the actual rotational kinetic energy itself, it will be increasing. We're still doing this torque in the same direction, acting to speed it up. It'll always be speeding up, it won't be slowing down. So this rotational kinetic energy is increasing.